So moving from there to the last piece of information out of this particular chapter, we have atomic mass. Now, atomic mass is different than mass number. Mass number was focused on the total number of particles in that nucleus. So that is, mass number is always a whole number, because you can't have a portion or a fraction of a neutron, or a portion or a fraction of a proton. Such things can't exist. But I can have, when it comes to atomic mass, fractional or decimal numbers, because we're not talking about a number of particles in this case. What we're talking about is an average mass. So when we talk about atomic mass, an atomic mass is, if you're looking at the periodic table, it is always the bottom number on an elemental box. So top number is usually atomic number in some kind of way. Bottom number is atomic mass. And those atomic masses are average masses. So if I take a scoop of carbon, and I'm trying to figure out what that carbon weighs, I'm going to use the average mass of carbon to help me figure that out. And that's where atomic mass comes in. Its calculation is a little bit complicated. Its calculation uses something called a weighted average. Now, if you're unfamiliar with weighted averages, because there are very few opportunities where you might actually run into them, weighted averages take into consideration two factors: the average mass, or excuse me, the mass of the isotopes themselves, and their relative abundances. So one thing about isotopes is that they are not all proportionally equal to each other in terms of their appearance. So, for example, carbon. Carbon has three well-known isotopes: carbon-12, carbon-13, and carbon-14. Those are the three most common isotopes of carbon. Now, those three isotopes are not present in the same amount. In fact, carbon-12, which is the most common form, accounts for nearly 99% of all the carbon on planet Earth. And carbon-13 represents almost all the 1% that is left. Carbon-14 represents a fraction of that 1%. Why the differences in abundances? Radioactivity. That the isotopes that are radioactive are not stable enough to stick around, and so we don't find them as often. So carbon-12 is not radioactive. It does not decompose. It does not decay in any kind of way. It stays as carbon-12. Carbon-13 and 14, both of those are radioactive. They will decay over time. Carbon-14 actually does so very predictably, which is why carbon-14 is used in what is called radiocarbon dating, which is used to try to estimate the age of artifacts, especially artifacts from living sources, things like plant matter, animal matter, wood, other kinds of things, where we can actually measure how much carbon is in it relative to a living species and make an estimate of how old it was or how long ago it died. This calculation, taking into consideration these average masses, like I said, it can be a little bit of a complicated one, because I have to factor in not only the abundance, but the mass itself. Now, there are a couple of tricks I can show you that actually make the calculation itself a little bit easier. But one thing I will say definitively, when we do these kinds of calculations, when you are told to calculate the average mass of a particular element, it's not just an average. You're not going to just take the however many isotopes, add them together, and divide by by N. That's not this kind of average. We have to take the weights into consideration, which is why this is a weighted average. So let's take a look at an example problem. Here we are told naturally occurring chlorine consists of 75.77% chlorine 35 and 24.23% chlorine 37. The mass of chlorine 35 is given here. The mass of chlorine 37 is given here. How do I do atomic mass off of this? So again, it's not average. I don't just take the 34.97 and add it to the 36.97 divide by 2. That would be what is considered a normal average. We don't want a normal average. We want a weighted average. So what I need to do is I need to take my mass and multiply it by my weight. So for chlorine 35, that calculation looks like this. For chlorine 37, that calculation looks like this, 36.97 AMUs times 24.23%. Now, if you follow along with the examples in your textbook, what they will do is they will take these percentages and they will divide them by 100 before they do the multiplication. I'm going to tell you why I don't do that. The reason I don't do that is because it is very easy, especially if you are looking at small percentages, to forget a zero somewhere. If you end up multiplying by the wrong value, you shift the decimal point by one spot either way, you end up getting the wrong answer. So what I'm going to tell you to do is we're going to eventually divide by 100, but we're going to do it at the end. And the reason we're going to do it at the end is to avoid that calculation error. And it's going to be difficult to forget that last step because the number that we're going to get when we do it this way won't make any sense otherwise. So 34.97 multiplied by 75.77. 4 sig figs in the mass, 4 sig figs in percent, 4 sig figs overall. So my calculator gives me 2649.67 and so on. I want the first 4 digits of that, so 2650. Gonna put a decimal point at the end of that just to show that that last zero is a good zero. It's a significant one. Unit there is still AMU. Haven't canceled anything out. 36.97 times 24.23. 4 sig figs here and here, so 4 in my answer. 895.8 AMUs. Now to turn this into a weighted average, I need to add these two numbers together. When I do so, 2650 plus 895.8 is going to give me 3545.8 AMUs. Couple of things I have to take care of. I just did an addition, so I need to apply the correct addition rule for rounding for my sig figs. So my first value was known to the ones place, the place before the decimal. My second value was known to the place after the decimal. So with this calculation, I can see I have 2 different estimated digits. I know by rule that I'm only supposed to have 1. So I need to round to the one that's furthest left, the one in yellow. So I'm going to round to this digit, which means I'm going to round up, since the 8 here is going to round up. So 3546 AMU is going to be the result of this calculation. Now I look at this and go, wait, atomic mass of 3,546. That doesn't make any sense. I can look at the periodic table. I can see that there's no more mass greater than 294 on that table. Where am I getting 3,500 and change? This is why we know that we will never make the mistake of stopping here. We haven't divided by 100 yet. We haven't taken into consideration percents. This is why I do it this way. This answer makes no sense until I divide it by 100. When I divide it by 100, I get 35.46 AMU, which if I look on the periodic table next to fluorine, it says 35.453. Yeah, we're pretty close. The difference between our answer and that answer there is rounding. But we're correct all the way up to that last significant figure. So this process is what we use to get any of those numbers on the periodic table. The only difference between the numbers that we might calculate and those is the degree to which that we round. So, our AMU, is our mass as precise as it could be? Well, in this case, probably not. Are these percentages as precise as they could be? Probably not. That's probably the difference between their number and ours. All right, any questions with this example problem? All right. All right, I'm actually going to skip this one, so forget that there's a responder here. This is a question that's asking you to basically work backwards through it. And I will tell you that I stripped out all of these questions for the whole one because I didn't see the value in working backwards through that. So we will just set that one aside. And so all that you need to do is fill out this last question. So how do you feel about isotopes and atomic mass? So give me a quick response right there. And then we will move on into chapter 5 in just a minute or so.